Welcome to ECEN 215 Principles of Electrical Engineering. Today we're going to do an introduction to capacitors. So what we're going to talk about today is introducing two new circuit elements. As we learned at the very beginning of the class, a circuit is composed of circuit elements. So far we've had power supplies of various kinds. We've had, constant DC or even changing voltage elements, basically creating a voltage. We have had current supplies to give us a constant current or a time rate of change current. We've had dependent voltage sources. We've had dependent current sources, both dependent upon either another voltage or another current. And we've had resistive elements, such as just a simple resistor that just absorbs energy. That's what we have studied so far. Today we introduce two new concepts. This is the inductor and the capacitor. These devices both absorb and hence consume energy as well as provide energy. They store energy effectively. We're going to start by a discussion of the capacitor, which stores its energy in the electric field, and the inductor stores its energy in the magnetic field. So let's just go ahead and get started. This lecture is a bit of a refresher of what you would have learned in your electromagnetics and physics. So this is going to be fairly elementary and not really introducing anything new that you shouldn't have already had before, but just sort of getting you caught up to speed so that we can now actually use these new elements in different circuits and see the effects of them. So again, what is a capacitor? Capacitor simply is two conducting plates separated by a dielectric, i.e. an insulator. And that's just simply all that this is. There's an electric field that is created between these separated metallic plates, and that is where the energy is being stored. Here's kind of a rough idea how a capacitor is physically created. This is an axial leaded capacitor. You've got metal foil, and you've got this dielectric material, and as it is rolled up and tighter, the capacitance increases. And we'll see the equation for determining capacitance here in just a moment. So a basic fluid flow analogy for a capacitor is this elastic membrane and a fluid channel. The fluid does not actually go through the membrane. I mean, in reality, if you have enough pressure pushing on the elastic membrane, there will be a point in which the membrane breaks, just in the same thing that's analogous to capacitor. If you increase the voltage or the electric field too much, it eventually will cause the dielectric material to break down and conduct. So effectively the same thing. So there's a very close analogy. So as long as this membrane is being held, the fluid on this side of the chamber does not actually move to the side of the chamber. However, as the pressure in this chamber changes, as we go from a low pressure, high pressure, so on and so forth, basically the pressure is causing a change. The fluid, hence, because this is elastic, is being pushed back and forth, causing there to be a current flow of fluid back and forth across this membrane. On this side, the fluid goes back and forth, and on this side, the fluid goes back and forth. The exact same thing is happening here with the electric field. This is very analogous to this solution. So just to have a slide on what several capacitors look like. These are your traditional, what we call through-hole capacitors that are usually mounted to a circuit board. These are surface mount capacitors. Again, they're mounted to a printed circuit board. This would be very common in your smartphone and your laptop, things like this. These capacitors can be about the size of the end of your mechanical pencil lead, so very small, have to be machine assembled. And then you have also capacitors like this. You have ones that are almost even larger than several trash cans in size, actually. Hold a lot of energy. This capacitor right here, for instance, you might notice if you've ever had to repair your air conditioner, this is like a start capacitor on a fan or a compressor for your air conditioner, for instance. Usually, just on a side note, because many of you will end up owning homes in the not too distant future. Eventually, you'll have to repair your air conditioner because it eventually will go, especially in the hot sun. An air conditioning repairman will charge probably a couple $100 to come out and replace this one little $2 capacitor. So just as a side note, the typical thing that goes wrong with your air conditioner system is usually the capacitor eventually dries out and no longer starts. And of course, hence your air conditioner is not working. Typically that is because the capacitor has blown or has just no longer is able to conduct energy or move energy back and forth. It's just no longer viable. It is broken. And you just replace this $2 part with a replacement and you're up and running. It's just like a couple terminals and you're done. Probably you spend more time getting the part than you actually do replacing the part. It's probably, like I said, about $2-3 fix and probably about 20 minutes of your time. So just on a side note. So schematically, a capacitor looks like this. So we've seen what they physically look like. This is the symbol we're going to use. Now, in the past, we've had where we've had the resistor. And I don't really have to draw it because you know it, but resistor we draw schematically as this. And I'm just showing it's an element that resists the flow of current. And we draw it where it has a voltage V of T like this. And of course, the current flow is this direction, and its I of t is like this. So this is the symbol for the resistor that we have used and have studied so far. And of course, this is now the symbol for the capacitor. Note the fact that the I of t and the V of t directions is exactly the same. We keep the V of t related to the flow of current, and we also have I of t is in the direction from the positive plate to the negative plate. So that's very important to pay attention to that. Also, you'll note that on this specific symbol, we have a flat plate and we have a curved plate. That is denoting the polarization of the capacitor, that the positive plate is the one that's a straight line and the negative plate's like this. In practice, there are different types of capacitors, and there are physically some capacitors in which the polarity can be shifted backwards, and it'll be two straight plates. The flow of current versus the positive terminal stays the same. So if the current was flowing in the opposite direction, then the bottom part of this capacitor would be positive. So it follows I of t, if you will. The reason I bring that up is that there are very special capacitors, electrolytics, for instance, in which they are known as polarized capacitors. And if you put them in backwards, in other words, you apply voltage across their leads where the positive lead has a negative voltage, for instance, then the capacitor will physically blow up. So this is very important. So now the question is, what is the charge? So the whole point of capacitor is to store charge, to store energy. So charge, Q, is equal to the capacitance, which is measured in farads, the units of farads, which is simply coulombs per volt, where coulombs obviously is Q, charge, and V being the volts across the capacitor. So the amount of charge that's being held in the capacitor simply is Q is equal to CV. Now the question is what is I of t? Now we looked a moment ago at the fluid flow analogy. So if the fluid is not has a static pressure, just P is constant for pressure, then the fluid flow would be analogous to zero because the membrane is not moving. Again, here I of t is related to charge and the electric field. I'm just going to give you a moment to kind of think what likely would be happening here. Okay, so what we have is I of t is related to the rate of change of voltage times capacitance, or in this case, the rate of change of charge. So dq dt. So as the charge of this capacitor changes, that's going to influence the amount of current that flows, quote, through the capacitor. Again, physically, the electron that's here is not the electron that would be here. We know that. But from a schematic and from a current flow mentally, I need you to think that the current is physically flowing through the capacitor, even though that's not what's really physically happening. The electrons are different. But fundamentally, it's causing a flow through the capacitor that's related to the rate change of charge. Hence, that if that's true, and as long as C is constant, that just becomes the ddt of CV, or the C being constants pulled out, and it's just the rate change of the voltage over time. So just a construction of the capacitor again, we have two plates that have a specific area, W times L, and this gap D is the distance between the plates. And that is specifically referring to, let me draw that here, the actual distance between the intersides of this plate. So it's not to the outside edge, it's truly to the inner side of the plates here. So this edge to this edge, this D right here. It's a little hard to tell with the drawing that we have here, but we're referring to this part as D. So that's very important that you know that, because sometimes these plates can be thicker on especially a larger capacitor, and it is actually to the inside of the plate that this is occurring. And that is related to a value called epsilon, which is the dielectric constant of the material, and times the area divided by the distance d. So as d decreases, as these plates get closer together, the capacitance increases. As you increase area, the capacitance increases. So you can see the relationship. One thing to note, there is a breakdown point. Dielectric material does have a point in which it breaks down and will eventually cause current to flow. I.e. a spark. So there's like a dielectric constant for air. If you bring two plates together in air, eventually, depending on the humidity in the air and all sorts of other conditions, you'll have a spark between the two and current will flow between the plates. The goal of a capacitor is for that not to occur. So there is a point in which you cannot put any more voltage across the plates. The electric field is too strong. So that's important to know. So that's why you cannot take D all the way down to zero, because obviously if D was zero, the plates would be conducting, they would be conducted together. So epsilon is in the units of farads per meter, and the surface area of the plates, of course, is meters squared, and distance is in meters. So here's some relative constants here. So we use dielectric constant for a vacuum, epsilon naught, which is 8.85 times 10 to the minus 12 farads per meter. And we get the relative, we have a table of relative values to actually determine epsilon we need in our equation, which is epsilon naught, which is this, times ER, and ER is from a table of various common dielectrics. For instance, air is 1, diamond's 5.5. I've never seen a diamond capacitor, for instance. That'd be kind of interesting. Mica and polyester, for instance, very common, 7 and 3.14, for instance. So here we have a simple circuit, and we're going to do a little quick example of the mathematics we just looked at for a capacitor. We have a power supply with a provided voltage, V of t. Notice now we have a t component in our voltage. And that voltage looks like this. It goes from 0 to 10 volts in 2 microseconds. So notice the time scale is not in seconds, but microseconds, and our voltage scale is in volts. So we go from 0 to 10 volts in 2 microseconds. We stay static at 10 volts for 2 microseconds and decay from 10 straight down to 1 in a straight line over 1 microsecond. So we go from 0 to 10, stay at 10, back to 0, and we're doing that across different time spectrums. So how do we plot the stored charge versus time? So let's do that. So first, let's go ahead and write what the equation is for this. So what do you think that's going to be? Now we could write mathematically, I guess we could create some weird function that approximates this curve, but it wouldn't exactly be this curve. In other words, we can do what's known as a curve fit. In high order mathematics, we do that, but there's no reason to do that. We can do something known as doing piecewise plots. So we start with the fact that we know that C is 1 microfarad, or 10 to the minus 6 farads, and then we write V of t as this function. It's multiple parts. For 0, for time less than 0, we're just constantly 0 volts. For 0 to 2 microseconds, we have a sloping curve, 5 10 to the 6 t, because remember, we're in microseconds, so over a period of 2 microseconds, we go up 10 volts, so at 1 microsecond, we're at 5 volts. It's a straight line, so just 5 to the 10 to the 6 t. Then we're static for 2 microseconds, from 2 to 4 at 10, and then 50 minus 10 to the 7 t is this slope and line, and that's just simply y is equal to mx plus b to determine that equation. And then, of course, from 5 all the way to infinity, we're stuck at 0. So now we have that, we can get our charge simply multiplying V of t times C gives us this. So our C is 1 microfarad. Now, notice they look exactly the same because you would expect that, because the only thing that's changing it is a constant multiplier. That constant multiplier is C. We're still in the same time scale, microseconds, but notice here that the vertical axis has changed its scale to microcoulombs and not volts. So it looks exactly the same, 10 microcoulombs is our peak instead of 10 volts. So very important to pay attention to that little change. And now, of course, V of t is this, and we can see that we get our graph, no problem. So now that we have V of t, our next step here is going to be to compute I of t. We're curious what that is. So what do you think we're going to do here? Well, we're going to use the formula we have, which is the rate change of voltage over time times capacitance. C is constant. I of t is equal to C dVdt. And we end up with this, 1 microfarad times all these functions here, taking their derivative in parts. So we take individual derivatives each part. I'll give you a moment to do that yourself. You can pause the video to do this, and then we'll just move on to what the example shows. Okay, so what we have is the first derivative is a 0. The next derivative is just the slope. Again, 0. These two are constant. In fact, these three here are constant, so they're always a 0. And this one here was 50 minus 10 to the 7t, but the 50 is a constant, so we just end up with the slope part. So it's just 10 to the minus 7. So these now become constant values themselves because the t went away. And of course, it's over the same time spectrum. Worked out, multiplying 1 microfarad times these values, we end up with 0 amps, 5 amps, 0 amps, minus 10 amps, and 0 amps. Plotted, that looks like this. From 0, minus infinity to 0, we have 0 amps. For the next 2 microseconds, we have 5 amps. For the next 2 microseconds, in which we were at 10 volts, there's no rate of change on the voltage, so the current is 0. And then we have a more rapid rate of change. We went from 10 volts down to 0 volts in 1 microsecond, so we have minus 10 amps being done. So what if we are now going to take a look at, we have I of t, but we want to know what dq, we want to know what the charge was or also what the voltage was. So simply, we're going to introduce differential equations here a little bit. So if you haven't had Math 308 and differential equations, I understand. This is just kind of a cursory introduction to that. The differential equations in this class are kind of simplistic, so it shouldn't get lost too easily. So we're just going to use simple algebra. We have I of t dt. So this was I of t equals dq dt, which just simply took dt, multiplied it by I of t, and we end up with dq is equal to I of t dt. So if we want to solve for q, we simply just need to integrate, and we do that. Q of t is equal to t naught to t, I of t, with some value of known charge at the beginning. So you either have to assume that there was no charge at the beginning at t naught, or you were told the charge was t naught at at time t naught. The charge was, say, 5 coulombs or something. And of course, correspondingly, if we're solving for voltage, we take the c to the other side. We end up with 1 over c. Same thing, I of t dt from t naught to t. This gives us our rate of change of voltage, now integrated, or of a rate of change of the current, integrated. And now we have to add the initial voltage, not initial charge, the initial voltage of the capacitor. So there will be several homework problems which are going to be given I of t or V of t and are asked, with this capacitor in this circuit, what is the V of t or what is the I of t? And you would have to compute that. Anytime that you're going to be starting with the capacitor and you're given the current and you're asked for the voltage or charge, you're going to need to have this given to you, or you're just going to assume it's 0. So what's the power across a capacitor? Well, that is strictly V of t times I of t. It's as simple as that. This equation, P is equal to V times I, or V squared over R in the case of a resistor, and of course I squared over R. All those equations still apply here. P of t is equal to V of t times I of t. Nothing's changed in our fundamental circuit analysis. We just now replace that with V times C dV dt. So V can be time changing, but you just need to do V of t times C dV dt, and you have your power. Work is the integration of power of time. But the interesting thing is if you work out the math on this integral here, you'll find out that this simply becomes work is just equal to 1/2 CV squared. So this is one of the main equations to memorize when you're asked how many joules is being stored in a capacitor at a given voltage. This would be what you would do. So if you have a capacitor charged at 10 volts, for instance, then you would take 1/2 of the capacitance times 100. Just 1/2 C times V squared. If V was 10, 10 squared. That's how you would get that. So this is an equation definitely to have memorized and worked out. Of course, again, always make sure you memorize that P is equal to V times I. You do not need to worry about actually working this out. This was given to you so that you can see how the mathematics works out to this. This is the main equation here. Last two parts of the capacitors is how they apply in circuits. How do we reduce capacitive equivalence, if you will, similar to what we did with resistors. Here we have capacitors in parallel. This works very analogous to resistors in series. Here we have common voltage across the nodes. So C1, C2, and C3 are all connected on their positive side, and the negative side are all connected together. Their capacitances add. So the total capacitance of this could be replaced with one capacitor that has C1 plus C2 plus C3. Now the interesting thing to note here is the dielectric breakdown voltage is the minimum of C1, C2, C3. This is very important in a practical setting where you're not dealing with ideal capacitors and you got real capacitors. There'll be a breakdown voltage on that dielectric material. When that happens, if this is say 50 volts and these are 100 and 150 respectively, if this capacitor, this voltage total across here exceeds 50 volts, this capacitor will break down, and it doesn't matter what happens, these capacitors are no longer in circuit. It's a dead short between here. So it is the minimum of C1, C2, C3. And of course the three currents branch, I1, I2, and I3 will branch through corresponding to their equations based upon their capacitance values. So Kirchhoff's current law is maintained, and the same thing with KVL. So series capacitance works equivalent to parallel resistance, and that the equivalent capacitance is 1 over the reciprocal. So you got 1 over C1 plus 1 over C2 plus 1 over C3 in a case of this three-staged capacitance here. And just take 1 over that, and that'll give you the capacitance equivalent. The voltage or the resistive equation that you learned for parallel resistors, where you had two resistors in parallel, that equation still works for two capacitors in series. So if I only had two here, it would be C1 times C2 over C1 plus C2. Very analogous to the simple two resistor equation that you learned for two parallel resistors. Mathematically, it works exactly the same way. Now, thing to note here, of course, V1 plus V2, V3, and because of that, this is a constant case where the dielectric breakdown voltage is increased to V1 plus V2 plus V3. So if you have a very high voltage application, you can increase and you can only have limited capacitors, you can increase the capacitance chain by putting them in series and distributing the voltages across your capacitors. So this is a good little trick to be able to increase the voltage of a chain of capacitors with a limited capacitance being that. So in this lecture, we looked at the concept of capacitors as a new type of circuit element. We talked about their ability to store charge and how they have a process of absorbing charge and then being able to bring back charge. So This is a new type of element. We introduced the mathematical concepts behind it, how they are created in practical use. And we also talked about how you can parallel and combine and parallel in a series different capacitor networks and what that actually entails in a total amount of capacitance, so basically the equivalent capacitance of a network, as well as what happens with the voltages when concerning parallel and series capacitance. Again, if you have any questions, please make sure you come to the Q&A sessions where we kind of delve a little bit more in deep, answer questions, and work problems. Thank you and have a wonderful day.